Hey everybody, this is Mr. Piercy and welcome to Lesson 6 in Unit 2 on differentiation. Today we're going to be taking a look at the product and the quotient rule. This is going to build off of the general rules for differentiation that you would have seen in Lesson 5. We're going to start by taking a look at the product rule, then we're going to look at the quotient rule, and then we're going to start blending them together and trying to see if how we can utilize these rules when we are looking at them from a graph or from not so much a table, but some symbolically, and of course just normal analysis. Here what you see is the product rule, and they're kind of giving you two different ways of writing it. The one at the top says we take whatever function f is and we multiply it to the derivative of function g, and then we add the sum of whatever the function g is times the derivative of function f. Gotta love announcements. So the bottom one is basically the same thing, it's just rewritten where they took the second part of the first statement and then wrote that first. We said the derivative of function f multiplied to whatever function g is plus whatever function f is multiplied to whatever the derivative of function g works out to be. They're not the same. This is an example of something from algebra that we would refer to as the commutative property. It's simply saying that the order in which we add things is not going to matter. So let's move on and see how we're going to take a look at these. Now the first one is really straightforward. This one's not going to be much of a challenge for anybody, I think, based off of what we're seeing for the product rule. So here, this is how I'm going to look at it. I'm going to say f prime of x is equal to, now the product rule uses function f and function g, and I'm going to avoid using f and g here for the two binomials that we have. Well, let's say that this is h and this is k, just to avoid any confusion. So what I'm going to do is I'm going to take the derivative of what I've labeled as h, and I'm going to multiply it to k, and then I'm going to take whatever h is and I'm going to multiply it to the derivative of k. And here, the derivative of the first binomial is just a 2, and that's going to get multiplied to the x minus 4 binomial. Then we're going to put a plus sign, so the general expression for h is going to be 2x minus 1, and the derivative of the second binomial is just a 1. Here what we're going to do is just do your normal distribution and combining any like terms that you have. So the first distribution gives me 2x minus 8 plus the 1 doesn't really do anything, so we just have the 2x minus 1. And when we combine our like terms, we're going to have 4x minus 9. Now for this particular one, because these are just two binomial expressions, you by now have probably had a ton of experience of taking two binomial expressions like this and distributing them. So we could start with function f just being, where we distribute those two terms together, giving us 2x squared, and then we'd have minus 8 minus 1, so that'll be a minus 9x, and then plus a 4. So this is what we would have for function f if we just distributed the binomials, and here we just use the power rule that we saw in lesson 5, where we just take the exponent and multiply it to the coefficient, and then we drop the exponent by 1, subtracting it by 1. So the first term here gives me the 4x that the product rule gave me, and the second term, the 9x, becomes a negative 9 when we take its derivative, and the derivative of a constant is 0, so we don't bother writing it. So here, either way that you approach it, you are going to get the same binomial, or you're going to get the same derivative regardless of how you do it. Now this one is nice. It was easy to do that way, but in a lot of examples that you're going to see, trying to combine your two separate pieces into one function not always going to be very feasible. So on the next example here, B, you could try the same approach and distribute the two quadratics together if you want to, but I'm going to just kind of keep things going with the product and the quotient rule as they were given to us. So here I'm going to identify the first trinomial as part F and the binomial quadratic as part G. So here when I say y prime, here I'm going to look at it as f prime times g plus f times g prime. And if you prefer it the other way around, you are more than welcome to do it. It's not going to change anything, because whatever we get for the first term and the second term, the sum of them will still be the same. So taking the derivative of the trinomial, I'm going to get a 2x plus a 3, which will be multiplied to the 2x squared minus the 5. And then the sum, the next part here, function f is just the x squared plus 3x minus 1. And I'm kind of running out of space here, so I'm going to shift it over here a little bit so I have a little bit more space to write. And the derivative of the second piece in this case is just going to be a 4. My music app on my phone randomly decided it wanted to turn on at that moment. So anyway, we get 4x cubed for the second component. I'm sorry, not cubed. My mind is now scattered from the distractions that I've had. It would just be 4x. There you go. I added 1 instead of subtracted 1 for some reason. Now we'll go ahead and do our distribution and see what we end up with. So here, distributing the two binomials, I'm going to get a 4x to the third power minus 10x plus 6x squared minus a 15. And distributing the second bit, we will get a positive 4x to the third power plus 12x squared minus 4x. And at this point, it's just a matter of combining your like terms. We do have two x to the third powers, and they're both with a coefficient of 4. So the largest exponent value will be 8x to the third power, followed by a positive 18x squared minus a 14x minus a 15. And there's the derivative of y. So that, in a sense, this is the gist of the product rule. Now here you can see that on the next examples that we have here, particularly on C, things start changing a little bit. Again, we're asked to use the product rule to find the derivative of the function. So here you can kind of look at this first part, label them however you want to, but I'm going to kind of keep with the f and g that was given to me by the product rule. So here in this case I'm going to say y prime will be equal to the derivative of the first part, in this case the derivative of cosine, doing that backwards, the derivative of sine in this case is going to be 2 times the cosine of x times the cosine of x plus the 2 sine of x, and the derivative of cosine is a negative sine of x. So here I'm going to get a 2 times cosine squared x minus a 2 sine squared x, and I'm going to factor out the 2, so that'll give me, in this case, 2 times cosine squared of x minus sine squared of x. And in this case here, some of us may be wondering, well, at this point, is this a trig identity? Now, the basic trig identity says that sine squared of x, or theta, plus cosine squared of x, or theta, is going to be equal to 1. And in this case, they don't match as a trig identity. So I'm not going to try to simplify the expression in the parentheses to be a 1. And I'm going to just conclude that this bit here is going to be the derivative. And the next one is going to get a little bit more complicated, and I certainly encourage you to try and pause the video and see if you can work it out in advance of me. But here, because of the inclusion of the e to the x power, we're not going to have a lot of like terms when we multiply through here with the product rule. So let's see what we wind up with. So here I'm going to say g prime of x, and here I'm going to just take the derivative of the first piece. So here I'm going to look at this as f and g. So the derivative of the first piece, the derivative of 3 to the ex is just 3 to the ex power. And the second part there will be a minus a 2x. And that will get multiplied to g, which would be x cubed minus 1. Now we reverse it. We take the derivative. We keep the first part, function f by itself. So there will be 3 to the e times e to the x power minus x squared times the derivative of g, which in this case would just be 3x squared. So now let's go ahead and distribute and see, do we have any like terms? And I'm going to move my equal sign a little to the left here because I think this is going to get a little long. All right, so let's see what we have. 3e to the x power times x cubed will give me 3e to the x power times x cubed. And then I'll get a minus 3e to the x power when I distribute it to the negative 1. And next I'll get a negative 2 x to the fourth power, and plus a 2x, and distributing the 3x squared in will give me a positive 9e to the x power times x squared minus, and in this case we'll have a 3x squared. Nope, nope, nope. There we go. I'm not paying attention to my exponents. Add the exponents and I get something to the fourth power. So looking here, it doesn't look like we really have much in the way of like terms. It looks like maybe I have something x to the fourth here and something x to the fourth here. And those really appear to be the only like terms that I have in the expression. Now I don't think there's going to be much in the way of convention when we try to write this in standard form, because I'm not going to try to determine necessarily what the overall largest term is. I'm going to just put the terms that have e together first. So I'm going to just start it off with 3e to the x power times x cubed minus 3e to the x power. And then we have plus a 9e to the x power times x squared. The x to the fourth powers will give me a negative 5 x to the fourth power, and then we have a plus 2x. And I think that it may not necessarily be in proper standard form, but I think that will be sufficient for at least demonstration of how you use the product rule. So one thing that you want to make sure that you are careful with is the product rule is not going to work out to be the same way like the limit rules look like. We can't just take the derivative of the first one and multiply it to the derivative of the second one. It won't work out for you that way. And if you want to test that out for yourself, go back to example A and try doing exactly what this is telling you not to do, and you're not going to get the same answer of the 4x minus 9 that we saw when we worked it out. So here the quotient rule is kind of a variant on the product rule, because if you notice in the numerator, we're still taking the derivative of one piece and multiplying it to whatever the original function was. But in this case, we're not going to take the sum of the two terms. We're going to take the difference of the two terms. And in the denominator, we're going to take whatever the denominator actually is, and it's going to get squared. So the expression that you see at the bottom is just a mnemonic device that works really well to help you remember what the product or what the quotient rule is. We say it low-d high minus high-d low over low-low, or just low squared. And that lets you know we're going to take whatever the low term is, multiply it to the derivative of the high term, and then we're going to subtract whatever the high term is, meaning the numerator, and we're going to multiply it by the derivative of the denominator. And of course, the denominator can't give you something that would be a 0, but we're not going to really see much in the way of issues with that. So I'm going to do the first one for you as an example, and then I'd like you to pause the video and try doing example B on your own just to see how you do. So here, for example A, if I say low-d high minus high-d low, low means the denominator, so I'm going to just take whatever the denominator's expression is. In this case, it's going to be x minus 5. And I'm going to multiply it to the derivative of the numerator. That's what the d high is. So that'll give you a 6x squared plus 8x. And the derivative of the constant is just 0, so that's what we end up with here. And then we take the high part, meaning just the numerator, so 2x cubed plus 4x squared minus 7, and we multiply it by the derivative of the denominator, hence the d low part, which in this case the derivative of the denominator is just 1. And all of that is over, and I didn't get that line very nice. That's going to be over low-low, or low squared, so I'll write it as x minus 5 quantity squared. So you do have to do your distribution and combine any like terms that you have in the numerator. So doing the distribution in the numerator, and of course here we're looking for g prime of x. And I probably really should just have an arrow indicating, because they're obviously not equal. So next, doing my distribution, I'm going to get a 6x cubed in the numerator, 6x cubed plus an 8x squared minus a 30x squared minus a 40x. And here, where the 1 on the end really doesn't matter, so we can just kind of distribute the negative to get rid of the parentheses. So I'll get a minus 2x cubed minus 4x squared plus a 7. And the denominator, we're going to just kind of keep it in factored form of x minus 5. There's no reason to try and expand that. We would want to keep it factored to see maybe it would have something in the numerator that it can simplify with. But now at this point, we just want to combine any like terms that we have. The x cubed terms simplify to be 4x to the third power then I get a negative 26x squared minus a 40x, and then plus a 7 over x minus 5 quantity squared. And the numerator is not really going to simplify in any kind of meaningful or easy way, so we're going to just kind of stop here and say, okay, well, that is the derivative of function g. So now go ahead and pause the video, try to work out example B on your own and see how you do, and when you're ready, hit play and see what my answer is. Okay guys, hopefully our answers are looking pretty similar. So starting it off up at the top, we are using the quotient rule to get this expression here. Now, before I distribute, what I'm recognizing is that the first term, meaning that this whole thing is I'm looking at it as one term, and this whole thing I'm looking at it as one term, they have a common factor of e to the x, so I'm going to just factor that out. And when I do, I'm left with the x squared plus 1 minus 2x in the numerator. And the only thing I do from the second step to the final answer is I just put the stuff in parentheses in standard form. So we wind up with, in the numerator, e to the x times x squared minus 2x plus 1 over that whole thing over x squared plus 1 squared. Now we're going to get into a couple of little interesting problems here, partly because these are going to be working with some transcendental functions. We have our natural log on example C, and we have some trig stuff on example D. Now the process that we're going to approach with this really isn't going to change. So I'm still going to do low D high minus high D low. So here, oops, I didn't mean to do that. I wanted to write it out, not have things just pop up. So here I'm going to say f prime of x, low D high. So low is x minus 2. The derivative of the numerator would be 1 over x, minus high, natural log of x, times the derivative of the low part, which in this case would just be a 1. And all of that is over low, which would be x minus 2 quantity squared. Now in the numerator, we're going to be able to see that the first two things on the left side of the numerator, we can write that as x minus 2 over x minus the natural log of x, because multiplying by positive 1 is not going to change anything. And overall, it's going to give us x minus 2 squared. Now, if you're trying to provide like some kind of numerical answer for your response question, we don't really need to simplify this all the way, but I'm going to go ahead and simplify this to where it'd be a little bit more proper. I'm going to look at this as x minus 2 over x over x minus 2 squared minus the natural log of x over x minus 2 squared, because we want to try to rationalize the numerator that's on the left side where we have the x in the that x in the bottom. So we're going to multiply the expression on the left by x. And of course, if I do it to the top part of the fraction, I have to do it to the bottom part of the fraction as well. And what we're going to see, this x and this x are going to simplify to be 1. And I'm going to be left with, overall in the numerator, I'm going to have an x minus a 2 minus the natural log of x. And in the denominator, we can kind of put them all back together as a common denominator, which would be x times x minus 2 squared. And that is going to be my derivative for function f in example C. Here, the next example on D, where we're using our trig stuff, same idea, low D high minus high D low. So here, y prime will be equal to 1 plus cosine of x, and the derivative of sine is going to be another cosine of x, and then we're going to subtract, so the high part, sine of x, and the derivative of the low part, well, the derivative of the 1 is 0 because the derivative of a constant is 0, and the derivative of cosine is negative sine of x. And all of that is over the quantity 1 plus cosine of x squared. Now, at this point, what I am going to recognize is that here, well, let's go ahead and distribute, and we'll start seeing things a little bit more clearly. Distribute the cosine of x on the left side of the numerator, and that's going to give me cosine of x plus cosine squared of x. And the signs, negative times negative, will give me a positive sine squared of x, all of it over the quantity 1 plus cosine, oops, I forgot my x, cosine of x squared. Now, what we're hoping that you're going to recognize at this point here, even though it's not, even though it's not written in the form that we normally see it, this bit here is a trig identity. Okay? So that bit right there is your basic trig identity where sine squared of x plus cosine squared of x simplifies to be a 1. So this gives me in the numerator, so this whole thing just simplifies to be a 1. So I'm going to write it as 1 plus cosine of x, so that way you can see that it'll match what we have in the denominator. And so we have common factors in the numerator and the denominator, so they simplify to be 1 over 1 plus cosine of x. And there is your derivative for y in example D. Here, what they're telling you that in this case the subtraction is not going to be commutative, so you do need to pay attention to the order that you do the numerator, low D high minus high D low. Here they're giving you kind of another mnemonic which I've personally never used. They have the high part still as being the high part, but they're calling the low part ho, like hi ho, it's off to work I go kind of thing. So you could use this one as ho D high minus high D ho, but over ho ho. But I know I prefer low D high minus high D low over low low. Maybe that's just because experience or whatever, but to me it just sounds better. But as long as you do it with the proper proper order, then you should be fine. So here I'm going to ask you to go ahead and pause the video and see if you can take what we've done so far and expand it a little bit, because what this one is asking you to do is not necessarily asking you to write or find the derivative necessarily. You do have to do that, but it's also asking you to extend it just a bit to write the equation of the tangent line at the point 0, 1. So go ahead and pause the video, try working this out, and when you're done, hit play again and see how your work compares to mine. Okay, so how did you do? The first part is, of course, making sure did you get the derivative correct. And this one was set up to give you a similar response to what you saw in the last example. When you take the derivative, low D high minus high D low, and you distribute in the numerator, you do see that sine squared of x plus cosine squared of x, excuse me, that trig identity, so that simplifies to be a 1. So I'm going to put the 1 in front of the negative sign of x, giving me 1 minus sine of x, so you could see very clearly that it will simplify with one of the expressions in the denominator. So the expression of the derivative is just 1 divided by 1 minus sine of x. So now I take that derivative expression and I find the slope at 0 for my equation. And, excuse me, sorry I had to pause it because for some reason. Plugging in 0 for the derivative, in the denominator, sine of 0 is 0, so we have an expression of 1 over 1, so the slope is just 1. And we're writing it at the point for when x is 0 and y is 1. So plugging it in a point slope form, we get 1 times, in parentheses, x minus 0, and then plus 1, or you could simplify that to just be x plus 1. So hopefully we're doing okay. The last bit there really wasn't anything new as far as writing the equation of the tangent line. It's just now we're using that quotient rule to be able to identify the expression for the derivative. Here, what we saw in the last lesson that showed you, we used the limit definition of the derivative to show you that the derivative of sine is cosine and the derivative of cosine is negative sine. Well, here we're going to kind of do the same thing to justify what the derivative of the other basic trig functions are. So we're going to look at cosecant, secant, tangent, and cotangent, so that way we can have their general derivatives, because these are going to be the derivatives of the trig operations, these 6 trig functions that you have. These are things that you're going to need to have memorized, because this is not something that you will be given. You'll just need to be able to say, okay, well, the derivative of this trig operation is this. Okay? So here, I'm going to go ahead and pause the video, and I'm going to just do the work here, and you can kind of write it out on your own as we need to. But we're going to start by recognizing that, for example, on A, cosecant is the reciprocal of 1 over sine, so that shows you how we're going to use the quotient rule. Same thing with secant, we're going to say 1 over cosine, so again, you can see how we're going to use the quotient rule. So I'm going to go ahead and pause the video and put the work out for these, and then, here in a second it'll pop up and you can kind of write everything down, or you can try working it out in advance of hitting play again to see how things go. But anyway, let's go ahead and pause and we'll restart here in a second. All right, guys, so how did you do? So down here at my little smiley face guy, let me find something here that won't be too obtrusive to identify it with. Here is our solution. For the reciprocal of cosecant, it is the product of negative cosecant times tangent of theta, or cosecant of theta times tangent of theta. And the one for secant of theta gives us secant theta times tangent theta. And those come about by using the quotient rule. This one would have been really, really challenging to try to do with the limit definition of the derivative. So that's why we kind of didn't, we held off until now to kind of take a look at these. So again, we're going to go ahead and move on to the last 2 for tangent and cotangent. And I'm going to do the same thing. I'm going to go ahead and pause the video and put the work here for it, so that way you don't have to sit through it. But again, I challenge you to, when you pause the video, or for you to pause the video and try to get to the conclusion before I do. So I'm going to go ahead and pause, and I'll be back here in just a second. Okay, excuse me. Okay, so here are the quotient rules that show what the derivatives of tangent and cotangent are going to be. And again, these are going to be just derivatives you need to memorize. So as we work through the quotient rule, in both cases, we are able to identify and utilize a trig identity. So they simplify to be a 1 in the numerator. On the stuff in red, we did have to factor out a -1 as a common factor in order to be able to see the sine squared of theta plus cosine squared of theta. but that gives us our respective derivatives. Tangent of theta is secant squared of theta, and cotangent's derivative is negative cosecant squared of theta. So here they are kind of written out. You can go ahead and fill those into your notes. And apparently when I typed them up, I had some issues. I had a couple of typos there when I typed them up. But let's go ahead and move on to our next examples. Now the next bit that we're going to be looking at here, these can be a little bit challenging as far as the derivatives are concerned. Here, what it's telling you, decomposing fractions with single term denominators using a constant rule. Here, the first one that we're going to be taking a look at isn't going to really be too bad, but I think the second and third ones, particularly the second one, I think can be a little challenging. But the first one, it is asking you to kind of rewrite it. So if I wanted to rewrite the first one, all I'm really going to do is just write it as y is equal to maybe in parentheses x minus 4 to the negative 1/2 power. And I can see very quickly that I can take the derivative of that just using the power rule. Now, we're bordering on something that's going to get into something called the chain rule, and we'll talk about that before the end of the lesson. But here, we don't have to worry about anything inside of the parentheses because it's just x to a power of 1. So anything that we would take to the derivative on the inside isn't going to matter because I would just have a 1. So what we have here is we just use our normal kind of power rule here. So the derivative of y, we would multiply the 1/2 to be in front of the where the coefficient is, in this case in front of the parentheses, and that'll give me x minus 4. And then when we say negative 1/2 minus 1/2, we get it to the negative 3/2 power. And so we simplify that with properties of exponents, so we wind up with y prime to be a negative 1/2 times x minus 4 in parentheses to the positive 3/2 power. And I wouldn't bother wanting to try and put that back into a radical form unless you have to try to evaluate it by hand if you're not allowed to use a calculator to try to evaluate that one. Now the next one is going to be a little bit more troublesome with the expressions that we have, particularly because of the e term that we have in the numerator, things aren't really going to simplify very well. So here, if I wanted to try to rewrite this one, I might just kind of rewrite it, where we could have, split up the fraction, and I could have x as a common denominator under both parts. And so on the left-hand side with the x terms, you can see we're just going to use, properties of exponents where we can subtract the exponents from each other, and that would give me 6x to the 3/2 power. But the term on the right doesn't really simplify. And if I wanted to try to use the power rule, I want to bring that x term up into the numerator, so that'll give me negative e to the x power times x to the negative 1 power. And you can see here with this is where we're going to have to use a product rule. So let's go ahead and do the derivative here. So y prime, the derivative of the first term, the 6x to the 3/2 power, we just use the standard power rule there, and so that's going to simplify to be 9x to the 1/2 power when we simplify that one. On the other part, we have to use the product rule, so we're going to say minus, and we'll take the derivative of the first part, which is just e to the x power, times the second part, which is x to the negative 1 power, and then we're going to add. So now we take the first part and we just leave it alone, but it's still just e to the x, and then we take the derivative of the second part, which would be a negative 1, basically, times negative 1. Oh, no. I'm lying to you here. That would be times negative x to the negative 2 power. And so you can see here that things aren't super pretty with what we have for the power rule. Now the first part, that's still nice, 9 times x to the 1/2 power, or if you want to write it as the square root of x, that's fine. And on the second part in the middle, I'm going to write it as minus e to the x power, and I'm going to move the x to the denominator so I can have it in terms of a positive exponent. And then we're going to do the same thing for the next part. Now the negative on the x is overall going to make this part here negative, and so that will be negative e to the x power over x squared. And that looks to be about all we're going to have on that one. Not very pretty, but that's what we wind up with. So let's take a look at the last one. Let me clear this off so I can move my screen down. And here, the last one here, I'm going to kind of look at it in terms of, if I rewrite it, where I'm going to look at here I'm going to look at the square root of x as x to the 1/2 power. So that way I can simplify it with the x terms that are in the numerator. So if I use the properties of exponents there, I'm going to get y to be equal to 6x to the, what would that be, 7/2 power, I believe. And then plus x, when I subtract the 1/2 there, that would be to the 5/2 power. And for the last one, minus 2, that would just be to the 1/2 power. There we go. And so now we're going to take the derivative. Now this one, even though the exponents aren't the prettiest looking exponents that we have, we can still use the power rule. So for the first one, we're going to get 42/2, which would be a 21x, and then we're going to subtract that, so that would be 5/2 for the exponent on that one. The next one would just be a 5/2 x to the 3/2 power, and then a negative 1x, negative 1, but that'll be x to the negative 1/2 power, so that'll put it down in the denominator to make it a positive exponent. And there is the derivative on the last one. So, let's see, I know we're getting long on time here, and I'm trying to go as quick as I can, but I don't want to lose you guys. So let's move on here. We are getting close to getting done, but what we're going to be looking at here next is higher order derivatives. And one of the things that's going to be a very common topic is what we're seeing here, position, velocity, and acceleration. So in Algebra 2 and in like physics and whatnot, and my pen has died on me. Give me 1 second. Okay, and let's see, is it working now? Kind of working. So, anyway. In physics and in some algebra classes, you've probably seen things like S of t is equal to, excuse me, negative 16t squared, and then it might say plus or minus some number. Here we would look at it as plus some number, which we don't know, but this is like a velocity, an initial velocity times time, plus like whatever your initial position is. And you look at it in terms of, okay, you have a projectile that you launch and it goes like this. Well, that's considered a position function, and if I take the derivative of the position function, we wind up with something called the velocity function. And if I take the derivative of the velocity function, which would be a second derivative of the position function, we wind up with something called the acceleration function. And that's kind of what they're looking at here when they're saying for the derivatives, where we have, you know, first, second, third, etc. Derivatives, and how they're kind of notated. So here, so here we're looking for f double prime of x. So find the second derivative of the function given what we have here. So here, I do have these typed up. I'm going to just go ahead and utilize what I have typed up here. The first derivative of the function would be negative, I'm sorry, not negative, but 9 over 2x squared plus 10x minus 6, just using the power rule. And then so the second derivative of that, we take the derivative of the first derivative and we wind up with 9x plus 10, and there we go. So for the next one, and again, I'm going to encourage you to pause the video and see if you can get the answer here before I put it up. But again, it's a polynomial, pretty straightforward. The only thing is that it's asking us for the fifth derivative, so it's going to take us a few rows to get through it here. So the first derivative is going to be negative 12x cubed plus 21x squared minus 10. Then I take the derivative of that to get negative 36x squared plus 42x. Take the derivative of that one and I get a negative 72x plus 42. So we're at the third derivative. So the fourth derivative would just be a negative 72. And the fifth derivative, the derivative of a constant in this case, would be a 0. Now in these next two examples, these are kind of interesting. And I'm going to kind of return your idea back to like imaginary numbers from Algebra 2 or Pre-Cal. If you had an imaginary number raised to some power besides like 4 or something, what do? Well, what happens is that we take whatever that exponent is and we divide it by a 4 just using old school longhand division, and I would look at to see what the remainder is. And based on the remainder would tell me what the I value would simplify to be. Like a remainder of 1, remainder 2, etc., and we would just see what it worked out to be. So here, and the reason why we divided it by 4 is because once we got to the fifth term that we did, we started seeing things repeat, so there was only 4 possible outcomes. And that's kind of what we're seeing here. I'm going to take here we want the 32nd derivative of sine of x. So if I take the first derivative of sine, I get cosine. Take the next derivative, derivative of cosine is negative sine. And then its derivative would be negative cosine. And then its derivative would put me back to sine of x. So at this point here, we can see that we're taking over a pattern where every fourth term the pattern starts to repeat itself. So here if I take the overall exponent value and I divide it by 4 based off of the remainders, these are what I can conclude it's going to simplify to be. So in this case, if I divide the exponent of 32 by 4, I get an 8, which has a remainder of 0. So that allows me to conclude that something with a remainder of 0, in this case the 32nd derivative, would be sine of x. And this is only going to be something that we can utilize with, you know, the trig stuff, because these are going to have repeating patterns that we would be able to take advantage of. And here it's asking for the 867th derivative, which is really ridiculous. But again, here we just work through it and see what the pattern is going to be. So the derivative of cosine, negative sine, its derivative would be negative cosine, its derivative would be positive sine, and its derivative would be cosine. And of course, now we see that we're repeating. We're back to cosine of x. So again, we're going to look at this in terms of our remainders. So I'm going to take 867, divide it by a 4, and see that we have a remainder of 3. So the 867th derivative of cosine, in this case, is just sine of x. And here is kind of what I was talking about as far as things that you would have seen previously. A potato launcher fires a potato downward, and it's giving us that quadratic expression where the only thing that we don't know is the initial velocity. So the 112, that's the initial position, being 112 feet above the ground. And we know the time that it takes it to hit the ground. We know time is in 2 seconds. So what it's asking us to do here, where distance is, where is it? What is it? Find the initial velocity. There we go. Find the initial velocity. I was looking for it at the end, but it's not there. So the initial velocity is v naught, and we're looking at it at 2 seconds, so that's what I'm substituting in for time. And here, just work through the basic arithmetic, and we're going to be able to solve for v just using normal algebra here. There we go. And so the initial velocity would be negative 24 feet per second. And we've talked about velocity itself being, it's akin to speed, but it is not necessarily going, negative doesn't mean that it's slowing down perhaps, it's just talking about the direction. So in this case, because we're going downward, that's why we have the negative velocity, or the negative 24 feet per second for our velocity. Now this last bit that we're going to take a look at here, this is where we're going to be looking at a couple of things where we're looking at it more symbolically, where we just know that we have certain things. So we're given that function f at 2 has an output of negative 4, its derivative at 2 has an output of 8, and function g at the same input of 2 has an output of 3, and its derivative would be a negative 1. And it's also telling us that f prime of 3, so the derivative of function f at 3 is going to be a negative 2. And it's asking you, find the derivatives of each of these things at x is equal to 2. So the first one, the first two on the left side, I should say, those are pretty straightforward. The product rule and the chain rule, those are things that we've been looking at here. So let's just go ahead and put these up here for you. We're just doing what we were given with the product rule, and in this case we get an output of 28. That would be the slope at that point. Quotient rule, low-d high minus high-d low over low-low, and I didn't quite give myself enough space here to see it. Here we get 20 over 9. Now the chain rule, I'm not sure why they're introducing the chain rule here, but the chain rule is something that we're going to really see in Unit 3. The chain rule is essentially saying that we're going to take the derivative of the inside part and multiply it to the derivative of the whole thing. So here the derivative of the whole thing is the 3 times function f to the second power, and the derivative of the inside part is just the derivative of function f. So for plugging in the values here, we know that at 2, x is going to be a negative 4 on function f, so that's what we have, and we were given that f prime at 2 is an 8, so that's why I'm substituting those numbers. And here, once you know what to plug in, it's just a matter of putting it into the calculator. So here for the chain rule on D, I'm going to take the derivative of the overall function and multiply it to the derivative of the inside part, which would be function g. Okay, so that's how I'm kind of setting this one up. So plugging in here, I'm going to plug in the 2 for the x's, and in this case, g of 2 has an output of 3, and g prime of 2 is given to be an output of negative 1. So now 3 becomes the input of the derivative of function f, which gives you a negative 2, and the product of those two is a positive 2. And if if I went over that quickly, don't worry too much. We're going to have a whole lot of stuff to do with the chain rule in the future. So the last thing that we're going to be looking at here is, can we do the same basic thing from a graph instead of, maybe like symbolically like we did on the last set of examples. So they're giving us this graph of these two functions, f and g, and it's saying that function h is a composition of f of g of x. So here, if I want to find the derivative of h, I have to use that chain rule where I say the derivative of the inside, which is what the g prime of x is, times the derivative of the whole thing, which is what the f prime of g of x is. So here we want to know what h prime of 2 is. So here, using kind of what we did on the last example, except instead of looking at it, with numbers that were given to you, now you have to kind of figure out what the numbers are. So here, g prime of 2 is going to be the slope of function g at x is equal to 2, or the slope of the tangent line at function g at x is equal to 2. And here, g of 2 gives us an output of 5, so the slope of the tangent line at x is equal to 2, that's about a 1/2. That's what that red line is. And so now I'm going to look, okay, well, what's the slope of the tangent line at function f when x is a 5? Well, at 5 there, we have a corner. And because we have that corner, we cannot take the derivative of the function at that point. So the derivative h prime of 2 does not exist. So here, moving on to the next one, find the derivatives of a graph from a graph. This is just looking at it and seeing what you come up with. So here we're looking at the slope of the tangent line of function g when x is equal to 2, and we already saw that to be about a 1/2. So here we repeat the process. The slope of the tangent line of function g when x is 3, in this case, is going to be about the opposite, about a -1/2. And those are the two lines that I'm kind of adding on the graph there. Here, finding the derivative again. Here we're kind of looking at it as a composition. So here we're not going to expand on what they're giving us. We're going to take function f and we're going to find its input. So function f at 7 has an output of 5. So now we're looking at what is the slope of a line tangent to function g when x is equal to 5. Excuse me, and in this case, I'm approximating it to be about a -3/4. And here, come on. Oh, my pen keeps wanting to die on me. So here, this is the last one that we're going to be looking at. Find the derivative of function h. And again, we have to use the chain rule. So the derivative of the inside part times the derivative of the whole thing is what we see typed up for us in blue. So here, I'm going to, for the derivative of g, I'm going to go to where function g is at 7, and I want to get the slope of the tangent line there. And I'm also going to look at the output of that. So I'm approximating these. These aren't necessarily the exact numbers. I'm just kind of approximating because at g of 7, it's not exactly at 3. It's just a little bit below it. So I'm saying it's 2.8. And I approximated the slope to be a positive 2/7. So now f prime of 2.8, the derivative of function f when x is just below 3, and again we're having to use a little bit of approximation here. That's going, since we have a tangent, or since we have a line segment there, the slope of something that's going to be tangent will be the same thing as the slope of the segment, which in this case is easy to identify as a -2. And now we finally take the product of those, and we get a slope of, or a final product, h prime of 7 to be a -4/7. So again, there's quite a bit of material that we had to go through, so I apologize for the length of the video, but I'm going to hope everything went well for you, that you're understanding it all. If not, we will discuss it when we meet in class. But thanks for watching. Take care, guys, and be good, be safe, and take care.